we're gonna find the domain. We're gonna show the asymptotes. Yes, we're gonna do a second example now. All right, we did this first one, A. Now we're gonna do the second one. Okay, so first, to find the domain and to find the vertical asymptotes essentially is the same exact thing. When you do the process at the same time, you find the vertical asymptotes and the domain. So, thank you. So, to find for both of them, so for domain and vertical asymptotes, it's essentially the same process. So I'm going to take the denominator and set it equal to 0. Now, this is basically what we learned in this class. How you then solve it, you have to pull from your knowledge of algebra, all right? You have to somehow factor and solve. But basically the process is always to set the whole thing equal to 0, then somehow factor and solve. All right, so you ask yourself, what can I factor out of this? Well, I can factor out a 2, and I get x squared minus 4 equals 0. So this is 2 times x minus 2, x plus 2 equal to 0.
It's then divide by 2.
Sometimes that works and sometimes that doesn't. This is one that always works. Okay, so x equals 2 and x equals negative 2. So at the same time, we've solved for two things. So now for domain, I say this is all real numbers minus x equals 2 and negative 2. That just stays. Basically when you're solving, you can divide both sides by 2 and that goes away. It's only the ones that are x plus or x minus that solve for. Minus 2 and negative 2. Okay, so that's what I did yesterday, and it's on the screencast from yesterday. Okay. Now, for the vertical asymptotes, you already solved for it. It's just x equals 2 and x equals negative 2. Right? So when you solve for domain, you also solve for the vertical asymptotes. Okay? Now, next. Let's do horizontal asymptotes. All right, for the horizontal asymptotes, okay, I'm going to take the term with the highest power from the top and divide it with the term with the highest power on the bottom. So it's going to be x squared over 2x squared, right? Those cancel, giving me just 2. 1 over 2, sorry. So the asymptote is y equals 1/2. Okay? So 1/2 here. That's the horizontal asymptote. And if I wanted to put up the vertical asymptotes, 2 and minus 2. Now, in order to graph two things that also help, all right, are the intercepts. Okay? So let's find the zeros. This is where the function crosses the x-axis. To do that, we set the numerator equal to 0. Okay? The numerator equal to 0. So what's the numerator here? X squared minus x minus 12 equal to 0. Is there any way to factor that? Well, let's see. X and x.
Yes, you can.
So to find the zeros, I'm going to set the numerator equal to 0. So two numbers that multiply to negative 12 but add to negative 1? Negative 4 and positive 3. So x equals 4, x equals negative 3. X equals 4, and x equals negative 3. At
What are we trying to figure out now?
Oh, we know 4 and 3.
where
Another point?
I'm looking for the points where it crosses the x-axis because that could be very beneficial to me. Okay. All right. Okay. So now so basically what we're doing is we're trying to get as much information as we can to help us graph. Another useful point is when x equals 0.
Wait, so it's a graph, so it's 4 equals 0. That's how you graph it.
Yes.
Why is it not 0?
Because these are when x equals 4, right? These are x values. Okay? It's x equals 4 and x
So
equals
if you plug
negative
in
3.
If you plug in for x, then it's y values.
Right. And it would give you a 0. Yeah. Okay. So now, if we plug in x equals 0, so when x equals 0, what is y? Right? Well, let's see. Y is, so I'm going to plug 0 into the whole thing there, into each of the x's in the main function. So what do I get on top when I plug in x equals 0? Negative 12 over negative 8. So how much would that be? 12 over 8. I divide by 4.
3 over 2.
Wasn't it?
3 over 2.
Wasn't it 12 over negative 8?
So when x is 0 and I plug it into the main function, right? 0, 0, negative 12. Okay. So when x is 0, how much is y? 3 over 2. So 1.5. Here. 1.5 right there. Okay? The green dot. Okay, now I think I have a pretty good idea. So what we're gonna do is this. Look at the vertical asymptotes, right? How many vertical asymptotes? 2. How many regions does that divide the whole grid into? 3. Okay? So now I have to see in each of the regions, right? Where is the graph? So in region 1 here, I have a point on the x-axis, right? And is that below or above the red asymptote? Below. So that means here the graph is going to be below the asymptote, hit that 0, follow this one, and go down there. Okay?
And then it has to go back up.
Now it's just like the Atari games. If it exits down here, then it must re-enter there.
Centipede. The game Centipede, I remember that.
Okay.
Then you go back up.
Now, okay, so now in this middle region, is there a point where it crosses the x-axis? Did we get a point where it crosses? No. So it has to go back up then, right? Because there is no way for it to cross the x-axis. So then it goes back up and right there. Okay? Yes.
How did you get negative 12 and negative 8?
So I plugged x equals 0 here. When x is 0, I have 0 minus 0 minus 12. 0 minus 8. Negative 12 over negative 8.
All you do?
That's all.
I don't understand the lines, the blue lines.
Okay, so basically,
When we were talking about horizontal asymptotes, okay, I said that if the numerator has a lower degree, right, then it's da-da-da-da-da. And then I said if the numerator has a higher degree, there is no horizontal asymptote. Now, we're going to revisit that. If the numerator has a higher degree, but it's only higher by 1, so for example, if it's like, if it's like x to the 4 and x cubed, or if it's x squared over x to the 1. If the numerator's exponent is higher by exactly one number, then there is what we call an oblique asymptote. Oblique means, previously we used to call it a slant asymptote. So basically it's a slanted line. Okay?
Oh, like you're oblique.
Now. Yes.
Oh,
Okay, now, how do you find that one? How do you find that one? Well, we use synthetic division to divide the numerator by the denominator. And then the depressed polynomial is the oblique asymptote. Okay? What do I mean by that? Yes, it's depressed. Okay. Because it's like compressed, depressed. You know, it's like pressed down. Okay. So, look. Okay. Let's do domain. You say x plus 3 equals 0, so x equals negative 3. So the domain is all real numbers minus what? Minus negative 3. Okay? This is what we were doing before. What's the vertical asymptote? X equals negative 3. Nothing new here. Okay? Now, horizontal asymptote. Is there a horizontal asymptote? No, there isn't. None, because numerator has a higher degree. The highest exponent in the numerator is 2. It's higher than the highest exponent in the denominator. The exponent in the numerator is 2, and the denominator is 1. Right? Now, it doesn't have a horizontal asymptote, but does it have an oblique asymptote? Yes, it has an oblique asymptote. And the reason is that the highest exponent here is 1 more than the one in the bottom. So, how do we find it? We've got to do division, either long or synthetic. So let's do synthetic division. Okay? All right. So what number is going to go on the far left here? Not 1. You take this, set it equal to 0, negative 3. Okay, remember? Yeah, sorry, on the far. Okay, and then inside we're going to have 1, 1, negative 8. 1 comes down, negative 3. Negative 2. 6. And negative 2. We don't have to end with a 0. It's totally fine. Yes. I ignore the remainder for oblique asymptote. Why? Because that's the rule. Now, I had started with an exponent of 2, right? So what's the exponent of this going to be? 1. So it'll be x to the 1 minus 2. Right? From here? You slap a y equals in front of it. That's your oblique asymptote. Okay. So now I'm going to graph this. I have one at negative 3. I don't have a horizontal one, but I have an oblique asymptote at y equals x minus 2. Do we know how to graph y equals x minus 2? Right? Y equals mx plus b. So where, oh my goodness. Where's the vertical, where's the y-intercept? At negative 2, what's the slope? Okay. So I'm graphing y equals x minus 2. This is the y-intercept, and that's the slope, up 1 over 1. All right? Huh? I'm graphing the oblique asymptote, which is what I got in the blue. Okay? No.
I'm good.
So this is completely. You start at the negative 2. Then you're figuring out the slope. And it's up one and over one.
Wait, how do you know it's up and over?
But to find the zeros, I need to set the numerator equal to 0, just to give me a couple more points. So let's set the numerator equal to 0. So I get, what? Does this factor?
No.
4 and 2, it doesn't.
No, it doesn't.
Okay, so now, if it doesn't factor, how do we know where it crosses the x-axis? It is the quadratic formula, but it's gonna, let's find an easier way. How about,
Oh my god.
how about the y-intercept where x equals 0? Okay? How about the y-intercept when x equals 0? So when I plug 0 in here, all right, so the y-intercept when x equals 0, right? If you plug x equals 0 into the function, into f of x, what do we get? In the numerator, I get negative 8 over 3, right? Negative 8 over 3, how much is that? In mixed number? It's negative 2 and 2/3, right? So negative 2 and 2/3 there is my y-intercept, right? Yes? Okay. So now, what I did here, I was trying to look for the zeros. It wasn't one that I could factor. Yes, you could plug into the quadratic formula, but it was gonna give me some irrational number, which, you know, do I absolutely need it? Maybe not at this point. So look, what we're gonna do here is this. Okay, so this has to follow the oblique asymptote like this, right? It doesn't touch it. So it has to follow the oblique asymptote, and down here it has to follow the vertical asymptote, right? Now, if it goes down here by the vertical asymptote, it has to re-enter here and there. Okay? That's how we do it. All right?
Oh, yeah, we would put almost there.
Okay.
So let's say we do this and we didn't draw that other line, how many points is it?
All right, so this leaves us with one other case. What if we simplify the rational expression and there are terms in the numerator and the denominator that cancel? Okay? Well, these are called either removable discontinuities or holes. So there is basically, like, from the outside it looks like a nice smooth curve, but when you zoom in, there is one tiny little point where there is a hole in the graph. All right, so how do you identify those? Okay, you see this function here. Let's factor it, okay, because now we see that, you know, both top and bottom can be factored. Let's factor it, and in the top I get x minus 3, x plus 3, and I get x minus 3, x plus 2, okay? Now, let's find the domain here for a minute. All right, let's find the domain. The domain, it would be when x minus 3 and x minus 2 equals 0. So x equals 3, x equals 2. So I say the domain is all reals minus 3 and 2. I'm setting the denominator equal to 0, just like I always do to find. Oh, plus 2, sorry. So negative 2 here, okay? Now, the next step is I would always say, oh, well, then there must be a vertical asymptote at x equals 3 and at x equals negative 2. However, there is a difference in this particular problem, and that is that when you go back to this reduced form, these cancel out. Okay? So now, there is still an issue at x minus 3. However, it canceled out. Okay? So what does that mean? That means, yeah, you got rid of it, so you're sort of like, it's like a band-aid. You go, oh my God, look, I got rid of the x equals 3. It's no longer a problem. So that means the x equals 2 never went away, right? So that means there is still a vertical asymptote at x equals negative 2, but at x equals 3, there's a hole. Okay?
How do we know that the x equals 3?
Because it's the x minus 3 term that canceled with the numerator. Right? Do you see here how it canceled with the numerator?
It's like you're taking it out.
Right, because you have the possibility of getting rid of it, essentially. It's not a full-on asymptote, it's just a hole. Okay? Okay? So, one more time. Initially, we had said that there was going to be a problem at x equals 3 and at x equals negative 2. And until now, we always said, oh, there's an asymptote at x equals negative 2 and at x equals 3. But now, not so fast. I can cancel out the x minus 3's. So yes, it's a problem, but it's a smaller problem. It's a hole, not an asymptote. Okay, let's see how this plays out in the game. Are there any horizontal asymptotes? Okay, so we go to the original equation. Okay, x squared over x squared is 1. So at y equals 1, there is a horizontal asymptote. So I go back to the original, and for horizontal, I gotta do the top of the bottom. And I'm doing that now. So at x equals negative 2, there is a vertical asymptote. Okay. All right. So at x equals 3, right? There is a break in the graph. There's a little hole in the graph. So how do I know where it is? All right. Okay. So to find the location, there isn't a set number. It's just however many comes up. There is no way to tell from the start how many you're going to have. So we're going to plug this into y. Okay? What is my the most reduced form of the equation from the top? Right. So let's plug 3 in there. So I know that somewhere at x equals 3, there's a little hole in the graph. But how do I know where it is? Well, that's what I'm going to find now. So let's plug, it's at x equals 3, but y equals what? Right? So 3 plus 3 over 3 plus 2. This one? I now want to plug it in here to see where exactly that hole is going to be. So it's going to be 6 over 5, which is like 1 point something, right? Right. So at 1 point something, notice how I'm not exactly like NASA precise with this. I don't have to be. Okay? So at x equals 3, but at 1 point something, there is a tiny little hole in the graph. At x equals 3, and at something, this number, there is a little hole in the graph. And that pretty much tells me how the function is going to look, because look, there, and there. Okay? Again, I'm not looking for NASA precision. How do we solve rational functions? All right, so let's move on from the graphing. So to solve these functions, we have to multiply each term by the LCD. Okay? All right. So, the first LCD is the common denominator. Lowest common denominator. All right? So, in the directions it says to state any restrictions. So for that, what you do is, where is the denominator 0? Okay, so there's only one here that has a denominator, right? And that denominator is x minus 6. What value for x would make that 0? 6. So if x is 6, we're in trouble. So I just sort of write it off to the side that, you know what, x should never equal 6 for this problem. Just let that hang there until you solve the problem. Now, this poor thing doesn't have a denominator, so let's give it 1. Okay? And you just say over 1. I didn't get rid of it, it's still there. Okay.
Wait, why can't it equal 6?
Because if x equals 6, what's 6 minus 6? You can never have 0 in the denominator.
Oh, yeah, that makes sense.
Right. Huh?
Oh, I get it.
Okay.
I thought that was, I get it.
Okay. So now, how many denominators do I have here?
1, 2.
2. I have a 1 and I have an x minus 6. What's the common denominator between them?
1.
Okay. So if you have a 1 and you have an x minus 6, the common denominator is x minus 6. So the way you do it is this. Okay. To find the common denominator, you look at all of the denominators that you have, and you take one of each kind. So if I have a 1 and if I have an x minus 6, I take a 1 and I take an x minus 6. So together, the common denominator becomes x minus 6. Yeah, you just take one of each. Okay. So now that I know this is my LCD, or my common denominator, I multiply every single term with x minus 6. Now, even the 0, because you can't discriminate against the 0, okay? It'll go away. It'll still be 0. We're just doing it for completeness sake. So now, here in the first case, I get x times x minus 6. Stay with me here. Here, in this, okay, minus. Yes, minus? Here, I have an x minus 6 on the bottom, x minus 6 on top. What happens to them?
0.
They cancel, you get a 1.
Wait, what about the 4?
The 4 stays.
Oh.
Okay?
Wait, so
Equals 0.
Wow.
Okay? Now look, you got rid of the pesky fractions. Okay?
Doesn't the 1 come into x minus 6?
It did. It's x times x minus 6.
Wait, but wouldn't you multiply the 1 on bottom also by x minus 6?
No, because if you have 3 over 5, let's say, times 2, you only multiply the tops with the tops and the bottoms with the bottoms. So this is like having x minus 6 over 1.
Wait, so if you wanted that to like this one up here, if you wanted it to be like 5 to find the common denominator, you would just put 2 over 5.
Right.
Then why would you have to
But we're not adding, we're solving. So we find the common denominator, but then we're not going to do anything else with that common denominator that we normally did. Okay? Okay. Let me do the next one and it'll set in. So now I have x squared minus 6x minus 4 equal to 0. Okay? Yes? Okay. Now you ask, is there any way to factor this? There doesn't seem to be. Okay? So what do I have to do? Quadratic formula minus 4 AC over 2A. So this is 6 plus or minus the square root of 36 plus 16 is what these days? 46, 52 over 2.
No, it's 15. No, it is 15. It'll be 13 or 2.
Yeah. 2 root 13.
I mean, yeah.
Now, at this step, if you can multiply everything on the outside of the roots by the same, if you can divide everything on the outside of the roots by the same number, you must. So we divide everything by 2, and we get 3 plus or minus 1 root 13 over 1, which is just that. Now, I'm going to do one more example, then take questions. Okay. Look at this next example. Is there anything that in the denominators that can be factored?
X plus 3.
This can be factored here, so I factor it. And I get x minus 6, x plus 3, yes? Now I need to find, first of all, what are my restrictions? What can x not equal?
Negative 3 equals.
X cannot equal negative 3, x cannot equal positive 6. If I get an answer that is one of those, then I need to make special considerations. Okay, now,
Wait, where does negative
Because it's plus 3 and minus 6, so then you do negative 3.
okay, LCD. Look at all of your denominators. What do I have as my denominators? I have an x plus 3, and I have an x minus 6. So I take one of each. X minus 3, I'm sorry, x plus 3, x minus 6. That's my LCD. Now, I need to multiply each of these by the LCD. I know.
Wait, so that's
Times
like,
both?
that's,
Whoa.
so that's like,
Can't you factor it
Ludicrous.
first?
That's Justin Bieber ludicrous.
It's really not as bad. Watch. It all goes away, I promise.
Why can't you just
Yeah, graduation.
X minus 8 and then factor that? And multiply that to 5.
That's what we just did.
No, you didn't. You broke it down. Why can't you just take it?
Because look at what happens now. Look at what happens now.
Oh, because you cancel out the 3 and 6.
Now, an x minus 3, I'm sorry, an x plus 3 cancels with the x plus 3. What cancels here?
Minus 6.
X minus 6. Here,
X plus
they both cancel. Yes. So now, from the first term, I have a 2x and an x minus 6 left. Then I have a plus 3 and an x plus 3. Then I have a equals 27. Look, the fractions went away. Okay, let's distribute 2x squared minus 12x plus 3x plus 9 equals 27.
So, will be 2x minus 9 equals 36.
Minus 9x. And then you bring this over and it's minus 18 equal to 0.
Why minus 15? What do you get minus 15?
Why do you bring it?
I need to subtract 27.
Yeah, I get it, yeah.
Now, I need to factor this. Okay, so let me show you.
Multiply by 2.
Let me show you the quick way to do it. Okay? So multiply the 2 by the 18, and I know, I'm going to show you again. X squared, no extra charge. I'll just show you again for free. Okay? Now, can I factor this? X minus 12, x plus 3, right? And then you have to put the 2 back. And now, what do I divide here by? 2? So what am I going to get? X minus 6, 2x plus 3 equals 0. Now let me solve these. So x equals 6, 2x equals negative 3, x equals negative 3 over 2. In the very beginning, like Yair said, we had said that x cannot equal 6 for this problem. So what do? You toss it out. That's called an extraneous solution.
Oh my god, so all that work for nothing?
So your only solution is x equals negative 3 over 2. Okay? Huh?